Hello everyone and welcome to class number 2. Today we're going to cover sections 1.2 through 1.4 as well as 4.1. That's linear versus exponential functions as well as rates of change. One other thing to note about the calendar, project number 1 is assigned today. So let's take a look at how we can find project 1. So it's inside of our Moodle page. If you scroll down, eventually you'll find a topic called projects. And right here it says click here to download the projects. And inside of here you'll find all 9 projects for the whole semester. Right now it's project number 1 that we're interested in. So you click on that and save the PDF, print it out, and work on it. So that's assigned today right now. And working with other folks on the projects I think is particularly helpful. So I've created a forum for project number 1 and for each of them actually. So if you're not meeting with folks in person, then maybe you can meet virtually here to talk about the project. And then once you're finished with the project, you're going to take a scan of it or a photo of it, somehow make it digital so that you can then click here to submit the project. And then I'll get a copy of whatever digital thing you upload and I can grade it and send it back with comments. So project 1 is officially assigned today. And that's this column. And then over here, it tells you when the projects are collected. And you can see that project 1 is going to be collected right here on class 5. Now you'll notice that I don't have the dates column. I've just hidden it. You guys have the dates column in your syllabus, and also you have this Excel document in Moodle. But I've hidden the dates. I'm not going to refer to dates in these videos. But in any event, the project right there is collected on class number 5, midnight of whatever date you have right there for class number 5. Okay, so that's the calendar. If you don't know how to access the calendar, watch the video for our very first class. That's 108 class 1, and that will tell you how to access the calendar inside of Moodle. Okay, so hopefully in front of you, you have this document, class number 2. If you don't have this document, go back to the video for class 1 and check it out. It will tell you that files for class 2 is what you're looking for. And inside of there, well, it's not there right now, but there will be a document, Word document, a PDF that you should have open in front of you. So, so let's take a look at this right here. Today we compare linear and exponential functions. Start off by doing the activity below. Answers follow. The growth of a city. Number 1. Suppose that a certain city had 10,000 residents in the year 2000, and since then it has grown at a steady rate of 500 people per year. Complete the table below showing the city's population T years after 2000. So what you're going to do is pause the video and you're going to fill in the answer to part A, but you're going to do a lot more than that. You're going to work through part B and C and D. And then number 2 describes a brand new scenario, a different city, and it also has a parts A, B, C, and D. So take your time, work through this. It's okay to use your calculator, especially for filling in this second table here. But work through all of this, pause the video. I really implore you to pause the video instead of just waiting. Math is not a spectator sport, so be active right now. Pause this video and fill in everything that you can on this page, and then come back when you're done. Okay, so hopefully you took your time and you filled in as much of this page as you possibly could. So I'm not going to fill in the answers here by hand because they're written out for you here on the next page. So this would be a good time to pause the video again and double check all of your answers and make sure that they all match the answers that are given here. Okay, so just a tiny bit to say about these answers. This one right here, let's make sure we understand where that function comes from. So 10,000 is the initial population, and then the plus 500t is because we gained, that 500 represents that we gained 500 people per year. And actually, I'm going to circle the whole 500t. I'm going to say 500t represents that we gained 500 people per year. And then we can come down to question number 2, part D, and we get this function. That one is tougher for some folks to come up with. So the 10,000, that's still the initial population, but now it's not a 10,000 plus 500 more people per year. It's 10,000, and then you're gaining another 5%. Turns out we multiply 10,000 by the right thing. And the right thing is this 1.05 to the t. So we can write in here that this part represents gaining, or I guess we'll say gained to be consistent, 5% of whatever the old population was per year. So that 1.05 is really 105%. Year after year, you end up with 105% of what you had the previous year. Okay, so moving on down here to number 1. Now that we've finished the activity, let's quickly review some of the fundamentals of linear functions. Linear functions have a constant rate of change, that is a constant difference in y values. The graph of a linear function is a, okay, so fill in the blank with a word. What's the graph of a linear function? It's a line. You can see the word line right there at the start of linear. Here are two forms of the equation of a line. Well, actually, maybe you could pause the video here and see if you know what I'm talking about. Write down two equations. They'll both have x's and y's in them, and come back when you're done. All right, so hopefully we came up with this thing, y equals mx plus b. That's called the slope-intercept form of a line. And an alternative is y minus y1 equals m times x minus x1. Point slope form of a line. There are other forms of lines that we're really not going to make very much use out of, but for example, ax plus by equals c is another equation of a line. There are lots of them. Okay, we'll fill in the blank in the next line for slope. So first of all, what letter do we use for slope? We use m. And then there are going to be a whole slew of formulas we're going to put in here. So pause the video and write down as many formulas as you can for the slope. Okay, so hopefully you've written down something. So let's see if we can come up with a lot of the same formulas. So in plain English, the slope is the rise divided by the run. We can make that a little bit more formal by saying that it's a change in y. That's the rise part, divided by a change in x. That's the run. We can make it more formal still by using a symbol that represents change in a lot of math and physics. That's this capital delta, the Greek letter capital D, delta y over delta x. Delta often stands for change. And we can get really down to the nitty-gritty and write something like y2 minus y1 over x2 minus x1. So that only makes sense if you know that we're talking about points that have this form, x1 comma y1. Those are the coordinates of one point. And then x2 comma y2 are the coordinates of a second point. Okay, continuing on. The units of slope are y units over x units. What were the units of the slope in our population example? Okay, so let's think about the population example again. So it's supposed to be y units over x units. All right, so the y is the dependent variable. So we got the y units on top and the x units on the bottom. But we didn't really have those two letters, did we? What letters did we have in our population example? Okay, let's see. So we had P of t and we had t. So P and t. So let's get them in the right order. So instead of y, which one did we have? We had P. That was the dependent variable. And instead of x, we had t. So the slope units must be P units over T units. All right, so let's write down the units for these things. So the P units, the population units, were people. And then the T units, let's see, that was time, and it was measured in years. So people per year must be the units for the slope. And what was the slope in our example? Well, let's go back up here. So let's see. In this equation, the 10,000 plus 500t, the slope is 500. So let's fill that 500 in. That's our slope. And see if it makes sense with the units we've assigned it. The slope is 500 people per year. That makes sense. That's exactly what the problem said. Okay, moving on down here, slope represents a rate of change. We'll talk a bunch about rates of change today. And very, very much of Calculus 1 is about rates of change. So certainly an important concept if you're headed to a calculus class. Number 2, find the equation of the graph pictured. Okay, this is a good time to pause the video and see if you can come up with an equation for that graph. Come back when you're done. Okay, let's see how we did. So the first thing I did was over there in blue. I used the y equals mx plus b form. If you prefer in black, you can use the point slope form, the y minus y1 equation. Either way, we should get to the same thing. So very quickly, we'll run through this. So if you're going to do the mx plus b form, you got to know the b. That's the y-intercept. Okay, so there's a gift given to us. It's right here. The y-intercept is -2. 0.0, -2 is right there on the graph. So it's easy to know that b is -2. You got to find the slope. Up above, we wrote down many equations for finding the slope. Ultimately, you're probably going to need 2 points, and those are the only two nice ones that I can see, only two with integer coordinates on them. So find the slope using those 2 points. We should get 2/5. And then just fill in the blanks in this equation. Y equals mx plus b becomes y equals 2/5 x minus 2. So that's the equation. And then if you prefer, you can use the point slope form. So the m is still the slope. You still need to find it by using 2 points on the line. And then the x1 and the y1, well, those are just the coordinates of any point on the line. And so you could pick this one if you wish. I chose this one over here. I wrote it in black. It's 5, 0. So instead of the y1, I put the y coordinate. It's 0. Instead of x1, I put the x coordinate. It's 5. So those are right down there. And then we just finish. Y minus 0 is just y. Distribute this 2/5 through, and we get 2/5 x minus 2. No surprise, we end up with exactly the same equation at the end, even if things looked a little bit different in the intermediate steps. Number 3, again, the slope is a rate of change, that 2/5. And in some sense, the y-intercept is an initial value. For population, the initial value is 10,000. That was this y-intercept right here, starting with 10,000 people, and then you gain 500 every year. So that y-intercept is an initial value. And here there's no context for this graph that we're given, but you could say that we start, if that word makes sense, at -2. And then you have a change of 2/5. Rise 2, run 5. Rise 2, run 5. Rise 2, run 5. Initial value and slope is pretty much all that you need to figure out what's going on with a line. When you're ready, we'll move to the next page. We now review exponential functions. Exponential functions have the variable in the exponent. F of t equals a times b to the t, where a represents the initial amount and b represents the growth or decay factor. So this equation right here is important. I'll highlight it. That's going to be our standard equation for exponential functions. Just like we have y equals mx plus b for lines, we have this thing highlighted in yellow for exponential functions. The important thing here is to note that the a and the b are constants. So there are just constants floating around on the bottom. The variable is way up here in the exponent. It's that t. Okay, so for the population example, we had f of t is 1,000 times 1.05 to the t. So hopefully we can match these things up. That 1,000 is the a. 1.05 is the b. There were initially 1,000 people in town. Oh, I think that's a typo. Didn't we start with 10,000? We did. My fault. But we'll go with what's written here. Initially 1,000 people in town, and the growth factor of 1.05 corresponded to a growth rate of 0.05, or 5%. So let's move on to number 5. It says write a function to model the population in a city with initial population of p sub 0, just calling it that, it's a constant, and an annual decline in population of 2% per year. So it's going to look something like this. It's going to have a p0 in it, and somehow that 2% decline is going to be important. So pause the video, see if you can fill in the blank with the formula. Okay, let's see how we did. So we'll write our formula here. You could call it P of t, you could also call it F of t. So let's see, in yellow there it says A times B to the t. A is the initial population. Initial population isn't given as a number, it's given as this kind of parameter, it's a constant. So it's just P0, and then there's a times B to the t, times. All right, I got to put something in here and then to the t. So somehow that decline of 2% is supposed to effect, what's in the parentheses. So if you decline by 2%, what number goes in the parentheses? Well, the number in the parentheses is the percentage that's still there, not the percentage that left, but the percentage that's still there. And if 2% left, then 98% is still there. So hopefully a bunch of you figured out that 0.98 is what goes inside of there. I'll write down a formula that we will see soon enough in this class. But if you're going to write down something like P of t equals, so we've got our initial population just like we saw before. And then instead of b, I'm going to put 1 plus r, and then to the t. And that 1 plus r is supposed to represent 1 plus the growth rate. So for example, if r is 0.05, a growth of 5% per year, then we have r 1.05, and it gets raised to the t. But in the example we just saw, the growth rate, well, let's see, it's not actually 0.02, it's negative 0.02. We were declining. And so if you plug in r equals negative 0.02, then you're doing 1 plus negative 0.02. And when you crunch that together, you get 0.98 to the t. So in general, it's 1 plus r. R could be positive if the population is growing, negative if the population is declining. Either way, it's 1 plus r. Number 6, what sorts of data tend to be exponential? Population growth, like we just saw, radioactive decay is a good exponential decay kind of problem. Compound interest is exponential growth. Biology, lots of population stuff, lots of things growing in biology. And sales also are often exponential. Number 7, we should be able to find exponential functions given 2 points. Let's do that for the pairs of points below. Okay, so we're going to do these two together. Let's start with part A. The points are 0, 100, and 216. So you can draw a graph if you want to. It's not really going to help. All you're going to do is see 2 points, and we're going to try to find a formula for an exponential curve that hits those 2 points. But you can draw the picture if that makes you feel better. Let's go ahead and start with our standard definition for exponential. We saw it up above. It's a times b to the t. All right, next thing to do is translate. The information in the points, we're going to plug into the equation. So 0, 100, that 0, what is it replacing? That 0 is the t value. So let's just make a note up here. This is the t, this is the output, f of t. Okay, so we're going to plug 0 for that t. So let's see, we got a times b to the 0 for the t. And then the 100, that's the output variable. That's the f of t. That goes right here. So 100 is a times b to the 0. And while we're at it, why don't we just go ahead and write down the other equation as well. So that's fine. So now we'll plug in 2 for t. So a times b to the 2 instead of t. And that's equal to 16. That's the output variable. So 2 equations, 2 unknowns. Hopefully we have enough tools to solve for a and b. Once we found a and b, we're done. We'll have our equation. Okay, this one is kind of nice because b to the 0, well, anything to the 0 is how much? Anything to the 0 is 1. So that b term just goes away completely, and for almost for free, we get the value of a. A is 100. And then all we have to do is plug in the 100 that we just found for a into this equation. 100 times b squared. And then solve for b. Okay, so we'll divide by 100. You could reduce that, but I prefer not to reduce it because the very next step here is going to be to take the square root of both sides. And 16 and 100 are both quite nice in terms of square roots. So let's take the square root of both of them. Actually, that was kind of silly. We can reduce. So reduce both of these guys. So 4 goes into both of them. So we get 4/25, which of course is still nice when you take a square root. And you take a square root of both sides. And we get square root of 4/25 is equal to b. Okay, one little detail. This is something that we mentioned in class number 1, but we just took the square root of both sides of an equation. And what do you have to remember to do? Whenever you take the even root of both sides of an equation, you got to put in that plus or minus. So b is equal to plus or minus. So the square root of 4/25 is just 2/5. So there we go. B is 2/5 or b is negative 2/5. Okay, here's a technicality. For exponential functions, to have the b be negative leads to all kinds of problems, and we never choose a negative b. So I'm just going to write here without really justifying it, reject negative. And we are going to content ourselves with the positive value for b. b equals 2/5. Turns out negative 2/5 for b will perfectly well satisfy these two equations right here. But it leads to lots of problems. We don't want to get involved in that. Okay, so then our final answer, just copying this equation again, but replacing the a and the b with the values we just found, is that f of t is, so we said that, what do we say, a was 100 times b is 2/5, that in parentheses, because it's all being raised to the t power, 100 times 2/5 to the t. And that's it. So what we've accomplished is found a formula for a function that hits both of those points, 0, 100 and 2, 16. Okay, moving on to part B, 321 and 754. Okay, we'll start this exactly the same way. It seems like the same process should work through this problem. A times b to the t is our standard exponential formula. Okay, that 3, is that the f of t or is that the t? So that 3 is the t. So a times b cubed, 21 is over here. And then the same thing for the second point, 54 is equal to a times b to the 7. So far, so good. Here's the problem. The problem is that we were given a gift in the previous problem that we're not given now. The gift was that in this equation right here, b to the 0 just became 1. And so even though it looks like you have two equations with two unknowns, really that equation has only one unknown because the b drops right out. But here, we're not so fortunate. We really do have two equations with two unknowns, and there's no way around that. Okay, so I think the most general way to solve two equations and two unknowns is this method called substitution. So hopefully that word rings a bell, and if not, then maybe it will ring a bell as we go through this process together. But the basic idea for substitution is to solve one equation for one variable and plug into the other equation. Just going to box our final answer from before. Okay, so we're going to solve one equation for one variable. So let's go ahead and just arbitrarily solve this equation right here. We're going to solve it, and let's see, is it easier to solve this equation for A or for B? Well, let's see, if you solve for A, it's one step, just divide. If you solve for B, it's two steps, because you have to divide, and then you got to take a cube root. And that sounds kind of messy. So I'm just going to solve for A, because it seems like it's easier to do that. Okay, so solve for A, and we get A is equal to 21 divided by B cubed. And then we're going to take that thing and we're going to plug it into the other equation. So this equation coupled with this new information. So 54 equals, I'm going to leave a space right there where the A used to be. And I'm going to copy the times B to the 7th. So inside of that space, instead of A, what are we going to put? Well, we've just discovered that A is 21 over B cubed. So this A right here must also be 21 over B cubed. And that's what we're going to put there. 21 over B cubed. So that came from that. Okay, and this is the best equation we've had so far in this problem because it has only one variable in it. So let's clean this up a little bit. So 54 equals 21, and then combining those b's, we know we're supposed to subtract those powers. So 21b to the 4th. And then we'll divide both sides by 21. And then take the 4th root of both sides. Technically, again, what should we put in? Because we just took the fourth root of both sides of an equation. Should put in plus or minus, but we're going to ignore that technicality because we never pick a negative value for b for exponential functions. Okay, so we've got our b value. We still have to find the a value. Best place to go here is the single equation that had a equals. So a equals 21 divided by b cubed. Okay, 21 divided by something cubed. What is the something? Something is what we just written up there. Fourth root of 54 over 21. So that's the value of a. We've got our value of b. So if we can put it all together, it's going to be a whole lot messier than the answer to the previous problem, but that's okay. So our final formula here is f of t equals, so it's supposed to be a times b to the t. A is the thing we just wrote down. Times b to the t times b is in the top right corner of this page. That's being raised to the t. Okay, it's not near as pretty as the other equation that we had, but this is our final answer. That right there is the exponential function that hits those 2 points. If you are really having some kind of adverse reaction to all of these radicals, well, I guess we can get decimals. So let's carefully type this stuff in. So I'll start here, fourth root of 54 over 21. So to get the fourth root, there are a couple of ways to do it, but one way is to type in the 4 first, because that's the root. Go inside of math, and then number 5 here. That x radical says you're going to do a general radical. That 4 is now the index. It's playing the role of the x. And then very careful with parentheses here, 54 divided by 21. So that right there is the value of b. And then 21 divided by that thing cubed is the value of a. So why don't we store that as b. I think store is one of the most underutilized buttons on the calculator. Just hit that store button right there. And 21 divided by b cubed, that's all I need. So 21 divided by alpha b to the third. So this right here is a. So we'll write our two numbers. Let's see, 10.34 and 1.27, we'll say. So that's a very good approximation for our exponential function. Okay, so it turns out there is a faster way to solve this problem, faster than substitution. I don't encourage you to use it, but I just want to show it to you. Suppose that we go back to our two initial equations, these ones here, and we're going to divide these two equations, one by the other, but let's actually kind of divide in the other order mentally. So you're going to take the bottom equation divided by the top equation. Okay, so on the one side we get 54 over 21, fine. What happens to these a's when we divide the two equations? Well, they cancel, and that's kind of nice. And then when I divide the b's, b to the 7 over b cubed is b to the 4. So I'll write it and then I'll quickly erase it. So we said we were going to divide in the other order. So 54 over 21 equals, and then the a's cancel, and we get b to the 4th when we divide the b's. And that equation took us a little bit longer to get to. I thought we saw it right down here. 54 over 21 equals b to the 4. So it's a cutesy little trick that happens to be more efficient. The reason that I'm not encouraging folks to use it is that it's a trick. It's kind of a one-off type thing, whereas substitution is a very robust technique for solving systems of equations. All right, when you're ready, move on to the next page. Number 8 is the definition. The average rate of change of the function y equals f of x from x equals a to x equals b is defined by ROC stands for rate of change equals f of b minus f of a over b minus a. So let's see if we can use that formula The average rate of change is just defined. That's why it's underlined at number 8. Okay, so we'll give it a shot in number 9. Compute the average rate of change of f of x equals x plus square root of x from, and then there's 2 different parts to this problem. So there's the curve here, that's the graph of this function, but don't worry about that for right now. All we're going to do is use the formula. So rate of change, according to the definition, is f of b minus f of a over b minus a. Okay, f of. Okay, so all we have to do is make a choice here. So normally the first number that you're given is a and the second one is b. So I'm just going to call 0a and 1b, but it's completely arbitrary. You can swap the order of that. You'll still get the right answer at the end. So for the choice I've made, f of b is really f of 1 minus f of a, that's f of 0, divided by b minus a, 1 minus 0. Okay. So now what we need to do is plug in and figure out what f of 1 is. So looking at the formula, f of 1, so plugging 1 in for those x's, 1 plus square root of 1, 1 plus 1 is 2. And f of 0, plug 0 for the x's, we get 0. And then just looking at part b, what's the other number that we're going to need to plug in for x? Okay, so hopefully we see that 4 is going to be important for us. We get 6. Okay, so I think we've got everything we need now. So all we're doing is looking at this piece right here, f of 1 minus f of 0. So f of 1 we said was 2 minus f of 0 is 0 divided by, and then on the bottom now it's 1 minus 0. So that's just 1. And upstairs is 2, downstairs is 1, so we just get 2. And that's the average rate of change. Okay, part B says find the average rate of change between x equals 1 and x equals 4. Go ahead and pause the video here and come back when you've done that. So hopefully we get 4/3 as the average rate of change there. Okay, so what's going on here? Well, there's a picture of the function. So let's think about plotting some points. So the first point up here at the top in red, x was 1 and y was 2. So that's the point 1, 2. I'm going to plot these points in green. 1, 2 is right here. It's kind of hard to see the numbers on the y-axis. The middle line in red says x is 0 and so is y. That's that point. And the last red line says 4 goes with 6. So that's this one right here, 4 with 6. And when we did this f of 1 minus f of 0 over 1 minus 0, well, that should sound like something that we've done before, that we've done today, actually. We subtracted some y values, and then we divided by, and we subtracted some x values. That's the slope. It's the slope of the line connecting 2 points, the first 2 green points here. So I'm going to draw a line connecting the first 2 green points. And the slope of that line is the rate of change that we just calculated. Slope of that line is 2. But then for the part B, it's a different 2 points. It's the ones with x equals 1 and x equals 4. So these are the second 2 green dots. So I'm going to draw the straight line that connects the second 2 green dots. And the slope of that line, the blue one, is different. Rate of change here is 4/3. So what's going on? Well, this is a way to really think about precisely what the curve is doing. The curve is not straight, so it doesn't have a constant rate of change. Like those 2 lines have constant rates of change, constant slopes. Black line, every time you run 1, you rise 2. The blue line, every time you run 3, you rise 4. But it's a changing rate of change for the purple. And calculus is all about rates of change, especially Calc 1. And in fact, in your calculus class, that formula right there is going to be really fundamental to you at the start. So I guess what we're saying here is that if we were to try to take the curve, the purple curve, and get from this point to this point, well, if you want to stay on the curve, you got to do, well, not quite that exaggerated, but it's a curvy thing. But if you just wanted to start here and end here, and you wanted to do it on a straight line, you would be changing by a slope of 2. But if you are looking at the changing, going from x equals 1 to x equals 4, well, here the curve isn't changing as fast. And on average, it is changing at a rate of 4/3. Okay, I'm just going to show you a real quick file on something called Geometers Sketchpad. So this is the graph that we were just looking at. Geometers Sketchpad is a piece of software. I'll talk about it after we look at this demonstration. So at the moment, the A is 0.24 and the B is 0.9. So I want to change these so that they represent, I want A to be 0, just like it was in the first problem. So we got to move that just a tiny bit to the right so it doesn't disappear. Okay, that's close enough to 0. And then B is supposed to be 1 in the first problem. So that's pretty close there. Okay, so taking a look at this, we are going from basically 0 to basically 1, which is what this first problem did. And the slope that we got was 2. And the slope that we get here is 1.84. That's close to 2. It's not exactly 2. It's because I'm not exactly on these points, but that's all right. But it's pretty close. And that's it. So there's that straight line. But then the next problem said go from 1 to 4. So now you're going to watch that straight line as it kind of flattens out as we run along this curve. So if I try to get near x equals 4, then we see this straight line, that blue line, and you can't even see the straight line. It's so close to the curve in here. And the slope of that line is 1.33, which is this rate of change that we found here, 4/3. Okay, so this Geometers Sketchpad it's a paid piece of software, and I certainly don't need you to spend any money on it. But it is possible to download a free kind of mini version of this software. There are some restrictions, but not so many that it's not worth downloading it. It's free, and you can play with this thing, and you can play with other things that I've created and other things that other folks created all over the world. So let me tell you how to access that software. So what you're going to do is go to our Moodle site. And somewhere towards the top, inside of this Get Oriented folder, you should see a document that says where to download free math software. And in there, it tells you exactly where to go to download the free version of Geometers Sketchpad. And then in order for you to access this particular document that I've created, you'll just need to go to our Moodle page inside of this topic, Material for the First Test. We're in class 2. That's where we referred to this Sketchpad file, and you can download it right there. Just download it to your computer once you have Sketchpad on it. GSP is the extension, Geometers Sketchpad. Okay, so coming back here, we can move on to number 10. It says functions can be increasing, which means as x increases, f of x also increases, or decreasing. As x increases, f of x decreases. Can linear functions change? What about exponential functions? What about other functions? So let's start with one of the other functions just so that we're really clear on what it means for a function to be increasing or decreasing. So I'm going to draw a parabola. Maybe we'll draw one that looks kind of like the one we saw in class 1. So what is happening with this function? Well, to be increasing means as x increases, f of x also increases. But to be decreasing, x is still increasing. So we do that to be consistent. And what that means is that when you're thinking about whether a function's increasing or decreasing, you always walk left to right. Everybody in the world, when they think about whether a function's increasing or decreasing, walks left to right. So as we walk left to right on the curve, let's trace out some dots here. So as we walk along this curve left to right, we get higher, higher, higher. The y values are increasing in this part. And because f of x is increasing, we know that the whole function is increasing until we get to there. So f is increasing. Until that point right there. And then something changes. So we're still going to walk to the right because we always walk to the right. But now as we walk to the right, what's happening to the f of x values? Now the f of x values are decreasing. And so we say the function itself is decreasing. So f decreasing. After that top point. So in the homework, you'll be asked some questions about where functions are increasing or decreasing. So let's come back and answer this question now. Can linear functions change between increasing and decreasing? The answer is no. If it's going up at one point, it's going up everywhere. What about exponential functions? Well, we haven't looked at graphs of exponential functions, and we will in a coming class. But I'll just draw a real quick sketch of the two different kinds of exponential functions. There are exponential growth functions that look like this, and exponential decay functions that look like that. And so you might think about, what are those functions doing? Are they increasing? Are they decreasing? Are they changing? Is it one of each? And try to answer the question, can exponential functions change between increasing and decreasing? Okay, number 11 says, if there's time, we'll play the Mathematica equation of a line game. So I just want to show you where this thing is. So if you go to Google and type in that phrase, equation of a line game with no spaces, and the very first hit you'll find is this thing at demonstrations.wolfram.com. Wolfram is the same Wolfram that we talked about before with Wolfram Alpha. So let's click on this thing, and if you're interested in it, I can tell you how to download this free software. So what happens here is you're given the graph of a line and then a bunch of choices, and only one of these is the correct equation for that line right there. So in this problem, let's see, we're going to find the slope. So the nice point here is there and there. So the slope is rising 2, running 3. So the slope is 2/3. So that's not the right equation because that slope is not 2/3. That one is. That's not a slope of 2/3. Neither is that, neither is that, neither is that. So I guess this is the winner because that's the only one that has a slope of 2/3. But also we need the y-intercept. It's -2, so that makes sense there. So I'm just going to do this one time. But as soon as I click go, then it's going to change the line and it's going to change my choices. And then this little timer is going to slowly tick down, and I have to try to get the right answer before the time runs out. And if I do get the right answer, it will give me a new graph and new choices, and the timer will go a little bit faster. The game ends when you either get the wrong answer or the time runs out. And then you get a score, and let's see how I do. You also get some dramatic music if you click this button here, so let's give it a shot. Okay, so the slope here looks like a -1/4, and then the y-intercept is -1, so we're looking for -1/4 -1, right there. And the slope here, let's see, we're going up 3, nope, up 4, and then that looks like a 5. So 4/5 x plus, oh, did I miss something? 2/3 x plus 1, there. And we'll do one last one. So this one is down 3/2, -3/2 x plus 4, but the time went much quicker. Let's see, -3/2 x plus 4, I think is that one there. So 341 points is my best score right now. So if you're interested in playing this game, here's how you do it. So likely you don't have the right software on your computer, but if you're here at GCC, some of the computers do have the software on it. But if you don't, if nothing pops up here, then you click on this powered by CDF technology. CDF stands for computable document format. So right here on this page, you're going to click on this Get Free Wolfram CDF Player. I've got the right version, so I've got a check mark, but if you're here, you probably don't. So choose, fill in these 2 blanks right here. Again, it's free, and start the download, follow the directions. If you don't want to do that right now, but you want to come back to downloading that, then go to our Moodle page, and I had mentioned a document about how to download free math software, or where to download free math software, and the directions for downloading Wolfram's CDF player are in here as well. Okay, and then the last thing is the learning objectives. I mentioned in the first video that I don't generally go through the learning objectives in the videos, but I'll do it maybe 1 or 2 more times just to really make sure that everybody understands the process, exactly what's due and when it's due. Okay, so learning objectives after class number 2. That number 2 is the same number 2 that we found at the start of the notes for today, right here, class number 2. And also, class number 2 is the same thing in this document right here. Class 2 is what we just covered today. So what are you supposed to do after you finish watching this video? Well, you go to Wiley+, you do the homework assignment titled Homework 2. That 2 matches that 2 right there. The homework is generally due 1 week after it's assigned. So it's officially assigned on this day, whatever date you have here. Add 1 week to that. That's when it's due, midnight of whatever date is 1 week away from this date right here. So coming back to this thing, so you're going to do the homework after attending class. You've got this list of things that I'd like you to be able to do. Read through them, check off the ones that you can't, work on the ones that you check off the ones that you can do, and work on the ones that you are having trouble with. Your class preparation is to read these sections. That's reading ahead. You might need to read the sections that we covered today again, but this is the reading ahead. You're going to answer these questions of the day. You're going to email me your answers by the beginning of class. That's next class. That's whatever date you have next to this class right here. That's when the questions of the day are due. And please, 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 in your email, put questions of the day in the subject line and the class number and your last name. For example, questions of the day, class 15, and then Smith, if that's your last name. So for this one, it'll be questions of the day 2, and then your last name. So number 1 is telling me about yourself. If you did that already, then you don't need to do it again. Number 2 is some vocabulary questions. You will find the answers to those questions in the reading. And if you go to the next page, do you have any questions about the reading? I always ask that. And then other things to do. So log into Moodle, that's the second bullet here, but also start working on project number 1. We talked about it earlier today. It is due at the start of class number 5. So one more time, class 5 is this one right here. Project is collected on that day. So whatever date you see right there, that is when project number 1 is due.